Hi everyone, my name is Shailesh, and I'm going to give you a presentation on introduction to FEKO, and also I'll show you how to design antennas and measure its parameters. So basically, to start with, FEKO is an electromagnetic simulation software used for various purposes like solving high-frequency electromagnetic problems, making wave propagation 3D models, analyzing radar cross sections, and of course, the most popular one is antenna designing. So FEKO basically works on method of moments, integral formulation of Maxwell's equation, and with recent updates and developments, like many more solvers have come up, like finite element method and time domain solver. So after starting FEKO using CSUN VPN, we click on Cat FEKO in the FEKO suite, then this screen pops up. So here we see quite a lot of things. Uh, to start our design, we use construct, which is this one, this tab. And then to create any solid, like a cuboid or a sphere or a cylinder, we can just directly click on it and then we can create it. So these surfaces, these are the surfaces which we can create above the solid, or it can be independent as well. And we can create lines as well, which is quite useful for creating dipole antennas. So, and we have these features here in modify section. Especially the union feature is quite handy when we have created a lot of things for an antenna, like connectors, patches, ground planes, and we want to kind of bring all together, so we can use this feature union. Um, so to give you a bit of heads up, what we're gonna do um, after designing our antenna is this one. We click on FEKO solver to basically solve all the calculations up, and then we click on post FEKO to measure the performances of our antenna, like voltage standing, wave ratio, reflection coefficient, which is known as S11 in some of the papers, gains, whether a Cartesian gain, or it can be using a polar graph, where we can also measure exile ratio, directivity of the antenna, and many more things using post FEKO. So I would like to watch out for the units, which is very important, which is right over here. It should be either millimeters or meters, depending upon the project you're working on. And the most important tool, which right here, which was quite handy for me, which is measuring distance and measuring angle. As I'll show you, one of the designs which I was following, which is this one. This is a microstrip patch antenna with asymmetric slits. So we have like these 2 points. So I want to measure the length of this point, this line. So I'll go to tools, and then I'll click on measure distance. So the most tricky part here is not enter the coordinates of the points, rather use control shift and put the cursor right on the point, and then leave it on the point, like the line which we want to measure, and this gives the distance, which is 0.28. So in the similar way, we can also measure the angle. Control shift and put the cursor on the point, and the second cursor on right on the angle, and the third one, which completes the angle. So in this way, it gives us the degrees, which is this is 38 degrees. So I'm telling these features as it can be useful for some of you, if you're making some design like this one. So now we will see how to design a 2.4 gigahertz half wavelength dipole antenna. So as this antenna is going to operate in the resonant frequency of 2.4 gigahertz, our wavelength turns out to be the speed of the light divided by the frequency. So we can start putting in the variables in the construction section. Uh, we can add variable like this. We can add the frequency first, which is 2.4 gigahertz in our case. So we add it, and then we add the wavelength, lambda, which is C0, which is the speed of the light divided by the frequency, and then we add height. Height is basically lambda, which is the wavelength, divided by 2, as we are designing a half wavelength dipole antenna. So we have all the necessary variables which we need to design our antenna. So now we go to construct, and then we click on line. As this is dipole antenna, so it is basically a wire which extends in z-axis. So we'll have our uv axis of the starting and end point as 0, 0. We make it 0, and we make the start point as minus h by 2 and the end point as h by 2, and we can name it as dipole create. So yeah, so we have created the wire, and then we create the port. Right on the middle. Then we add the voltage source to this port, which will be 1 volt and 50 ohms. This is a typical parameters which we take for all the antennas. Then we add the frequency. As this is a dipole antenna, we take a single frequency, which is 2.4 E9, which is 2.4 gigahertz. Now we request far fields. This step is very critical as we want to measure the gain, exile ratio, and things like directivity. This can all happen by requesting far fields. We're going to make a 3D pattern of the antenna, and then we create the mesh as our final step of designing. We need the wire segment length, as this is a dipole antenna. So we can take it as lambda by 20, and then we take our radius as lambda by 1000. So we are pretty much through with our design of antenna in CAD FEKO. Now we request for FEKO solver. We'll save the antenna as okay. So this is done, and then we start our post FEKO. So this is our model. If you want to see this model with a nice 3D view, we would expect something like a donut shaped around the wire of the dipole antenna. So we are going to click on 3D view, standard configuration 1, and then we'll add the result of far field 1. So yes, this is the donut shaped to radiation pattern around the dipole antenna. We can convert the total gain into dB by clicking over here, and then we can see we can also animate uh, this thing, and then like click on play. This is very useful for analyzing the wave propagation models. For example, we have a dielectric surface, and then we want to see how the wave gets reflected and how the waves are transmitted through it. So to move forward, on home, if you want to see a 2D Cartesian graph of the gain, we can click on Cartesian. We can request for far field. So here is the gain at 90 degrees. If we can also change the axis as per our convenience, maybe it can be frequency. So as you can see, we get the gain at 2.4 gigahertz. So it means our antennas is designed for 2.4 gigahertz, and we are getting the gain at that particular frequency. We can also make it as theta if we want to see. We can make it to decibels as well, and then yeah. After this, we can also measure the performance of the antenna using polar graphs. We can do it by clicking over here, and then we request for far field 1. Okay, so this is the theta half of the graph. If you want to see the full polar graph, then we have to click on theta wrapped. And then we can change the degrees as per our convenience, like whichever degrees we want to measure the performance of the gain. We can also look at the directivity, electric field, and likewise we can see many more features in post FEKO. Also, uh, we can change the parameters on the fly in the CAD FEKO, and then like do the FEKO solver there, and then click on post FEKO, and then again we see different results. You can also tweak the parameters in post FEKO to get the intended result. So this is pretty much it for the dipole antenna. Now we will move on to microstrip patch antenna. So these are the various types of feeding techniques which one should know before getting into microstrip patch antenna designing. So these are inset feed, center feed, and offset feed. So the most commonly used in microstrip patch antennas are the center feed. Sometimes also they use the inset feed along with the center feed, which kind of looks like this. This distance is basically called the inset feed, and then we have offset feed, in which the strip line can be adjusted on the x-axis according to the user requirements. This is quite a good method actually to feed an antenna, as this improves the bandwidth. So we will now see how to design a microstrip patch antenna with offset feed. So our antenna is going to operate on 2.4 gigahertz with FR4 substrate material, which has a dielectric constant of 4.4, and we can also take the loss tangent as 0.02. So to obtain the dimensions of the antenna, we use these formulas. We basically find the width of the patch by plugging in the resonant frequency and the electric constant of the substrate material, and then we find the finalized length of the patch using all these formulas, and then we finally make a layout of our design, which is quite handy while we are designing our antenna using CAD FEKO. So in this, as you can see, we have already decided the W, which is the width, length is L, and offset length can be anything as per the user requirement. So now, as you have seen in the diagram, the dimensions of the antenna. So we'll start creating our antenna. First of all, we'll change the model unit to millimeters over here, and then we start adding the variables. So the first one, let's say the length of the patch, which we found out, which was 28.38, and the width of the patch, which is 38, and then offset. Initially, we take it as 0, and then later on, we can change it to any number we want. We take the width of the substrate as twice the length of the patch. Length of the substrate as twice the length of the patch. Then we add our minimum frequency as 1 gigahertz and the maximum frequency as 5 gigahertz. The width of the microstrip line, which is 3 millimeters, and then the length of the microstrip line, which is 15. Okay, so yeah, finally the height of the substrate as 1.6. So we have pretty much created every variable which will need further designing. So now we start creating the substrate, FR4 substrate using cuboid. So we'll take our definition method as base center. We won't touch the base center for now. We'll change the dimensions to width of the substrate and then length of the substrate, and we'll take it as minus h. Why we're taking it as minus h is because we want our z-axis to be positively facing from the patch. This can vary. I mean, this is quite useful for me, as later on I don't have to change my axis, which due to which I'll get my results in polar graph very easily. We'll change it to subtract. There we go. We have created our subtract, and then we'll change the medium using dielectric medium. So FR4 is 4.4 and the loss tangent is 0.02. The label, we can label it as FR4, and then we change the medium to FR4. So there we go. We have our substrate of FR4. In this way, you can add any substrate with any permittivity and with the respective loss tangents. So now we start creating the patch using polygon. Some of you can also design using a simple rectangle, but I prefer this method as this is much easier and convenient, and it's quite accurate also. So we start creating our patch right from this corner, and then we'll create it like this, and at the end we'll come here. So the U, which is the x-axis, it'll be starting from left of this straight line. So it'll be simply minus WF by 2 plus offset. As we are creating an offset microstrip line, so the offset will be moving on the right hand side. So that's why this is plus offset. And then our V axis is minus LS by 2, which is half the length of the substrate. And then there is no Z axis, so it's 0. So in this way we create our corner 2, which is again minus W by WF by 2 plus offset. This will be minus LS by 2, and it'll move further up from here to here, which is the length of our microstrip line. So plus LF. Again, our z-axis is 0. The corner 3. So we want our line to move this side. So it's basically minus x-axis. So it'll be minus width of the patch. Therefore, it is minus W by 2. The V-axis remains the same as the previous one, as there is no change in it. So it'll be minus LS by 2 plus LF. Now we add one more corner. So we want our point to move, our patch point to move upwards. So we take it as same U-axis, but a different V-axis, which will be plus the length of the patch. Okay. And then we want the point to move towards right, where our y-axis remains the same as the previous one, which is minus y2. Our u becomes minus w by 2 plus w. So in this way, we keep on creating the corners. So now we will move on left hand side plus offset, and our v remains the same. Okay, so it's slowly starting to shape up, as you can see. There you go. It's right there. You can rename it as patch. So we have created our patch. So now we will reunion these two things so that we can change the material over here, and we can change the medium to a perfect electric conductor, the patch and the ground plane. So I want to see which phase my ground plane is on. It's phase 1 and phase 8. So I'm going to click these two, phase 1 and phase 8, and then change. Okay, so design is ready. So now to create a port right over here, we need to extend this corner. So we'll do this using a rectangle right on base corner. And then we take our base corner as minus WF by 2 plus offset. Then our width is the width of the microstrip line. Rename it as extension 1. So as you can see, we have created the extension of the microstrip line right here. So we will now create the same thing at the opposite end. From here, copy and transfer it. So there we go. It's right on the opposite end. And so now we want to connect this using two similar type of rectangles. So now we will copy the first one. Copy. Then we will change the starting point, let's say to 0.8. It doesn't like it, so it can be. It should be a number which fits in, let's say 1.6. Yeah, that's better. So the height should be h by 2 as we are going to rotate this thing. Yeah. So, okay. So now we will rotate this thing 90 degrees using transform, rotate. Our starting origin is the same as the previous one. So we'll take this, and our V is this. Okay, so as we want to move the axis to 90 degrees down, so we'll take the U as 1, 0, and 0, and this as 90 degrees. So now you can see it has successfully rotated to 90 degrees downwards, and we are going to create a similar type of rectangle to connect these two rectangles using copy and translate, which is right here. Take it as 0, 0, 0 to minus of our height. Okay. So as you can see, it's right there. We have created the extension of the microstrip line. Now we will choose this. Okay, before doing anything, we will do a union of all these things. In this way, it's easier for us to further move. Okay, now we'll choose the edge which we are interested in, which is to create a edge port. So the edge is this one. So right here we'll create our edge port. So we'll move this face to the negative side. And create. So now we'll add the voltage to our port. Then frequency. This should be a linearly spaced discrete points. And let's say like 100 points maybe. Get a continuous waveform. So as we are creating an offset microstrip patch antenna, so we are going to set our offset to any value such as 3. So we see our microstrip line shifting towards right. Maybe we can set it to 6, which is much, yeah, this looks good. And then we'll request far fields, which is quite important to measure the gains and exile ratio and directivity kind of things. And then we'll mesh our antenna. And then we start solving using FEKO solver, which will take quite a bit of time as we have requested for 100 number of frequencies. So after which we will move on to post FEKO. So after successfully finishing the FEKO solver, we now start with post FEKO. If you want to see a three-dimensional view of our antenna radiating, so we have to click on standard configuration and 3D views, and then click on far field. Okay, so this is our gain. We can change the quantity as per our requirement, like directivity, which is in dB. We can click on exile ratio. which is pretty much linked to the polarization of the antenna. If we want to see a 2D Cartesian, then we have to click on Cartesian and then request for far field. If we have to measure the gain, yes, this is the gain. It should be in dB. And also we can measure other quantities in a 2D graph like XL ratio, which is like this, activity. We can also view the polar graphs. We can request for far field and then theta wrap for a full, and we can change the phi as per our requirement. And see how the gain changes. It should be in dB as well. So in this way, we can also measure the directivity at different phi and different frequencies as well. So if we have to measure the reflection coefficient, we'll click on Cartesian and then we'll import the voltage source. Yes, so this is the voltage source and we have our reflection coefficient in dB. So we see our antenna resonates at 2.4 gigahertz, and then if we reduce the width of the microstrip patch line, then this at 2.4 gigahertz there will be more reflection coefficient and there will be lesser resonating frequencies at these ends. In the same way, we can also measure other quantities like current, voltage standing wave ratio. So this is the impedance which you can measure, and admittance. So in this way, you can measure anything as per your requirement, as per your project. So yes, this is pretty much it, and I hope you found my video really helpful. Thank you very much.